Welcome to this explainer. Look, we need to shatter a massive illusion right off the bat today. Clean code and a perfectly green CI pipeline are absolutely not enough to survive modern production environments. If you spent any time building distributed systems, you already know the brutal truth. What works perfectly in staging can and will fall apart the second it meets real-world chaos. Today, we're going to dig in together and uncover exactly where these silent failures are hiding. Let's set the scene with a reality check we have all faced. It's Friday afternoon. Your unit tests passed, Jenkins is glowing green, the deployment was a so-called success, but suddenly your entire checkout system is returning 403 forbidden errors to every single user. The code is technically alive, sure, but functionally, it's dead. Why does this happen? Well, it's because modern performance and reliability are systems properties, not just local code properties. Section 1. Seniors delete, juniors add. The code deletion paradox. To understand why these distributed architectures fail, we actually have to look at the massive difference in how code itself is treated. A junior developer's contribution graph usually looks like a mountain range, celebrating tens of thousands of lines of new code, complex abstractions, and shiny features. But a battle-tested senior engineer's graph, it looks like a valley. They celebrate deleting code, ripping out redundant microservices, and collapsing unnecessary layers. Why? Because cognitive load is the real enemy. Every single unnecessary line creates dependencies. You know that incredibly clever abstraction you're writing today? Ask yourself if you honestly want to be the one spending 3 days trying to debug it next year, when the system is literally on fire. Senior engineers ruthlessly delete code because they know every line is a liability that's going to drastically slow down future troubleshooting. Moving right along to Section 2, the latency lie. Why averages hide disaster? Okay, moving from the code layer to the network layer, we need to completely destroy the concept of average latency. If you're tuning your architecture based on averages, you are flying blind. Just look at this staggering number, 30,000. At hyperscale companies like Uber, a single ride-hailing request from a user doesn't just hit one server and return. It traverses hundreds of services and initiates over 30,000 remote procedure calls. At that massive scale of distribution, latency isn't a static metric anymore. It's a combinatorial explosion. Which brings us to a foundational insight from Google engineers Jeff Dean and Luis Andre Barroso. In large systems, rare slow events are no longer rare. Because of this insane scale, measuring the average speed of your service is absolutely useless. An average completely masks the P99 tail latencies. Those are the rare, slow requests that actually trigger massive cascading timeouts across your whole system. If 1 in 1,000 requests takes 3 seconds, and every user action triggers thousands of requests, then literally every single user is going to experience that slowness. So to eliminate this network tax, senior engineers are shifting away from chatty REST architectures. REST over HTTP 1.1 suffers from head-of-line blocking, where one slow response stalls everything else on the connection. By moving to gRPC, we leverage HTTP2 multiplexing, incredibly compact binary serialization through protobuf, and compressed headers. It's a fundamental architectural shift to basically hack the literal physics of moving data over a wire. Section 3, Container and Orchestration Nightmares, deep within Kubernetes. Now, even with flawless code and perfect network protocols, the infrastructure layer itself is hiding some pretty silent terrors. Imagine this. It's 10 a.m., your payment service starts throwing 502 bad gateway errors. You check the dashboard, and your pods are continuously dying. The restart count is climbing rapidly, but when you run kubectl logs, it returns absolutely nothing. The underlying worker nodes have plenty of CPU and RAM, and there are 0 failed liveness probes. Your application is dying in total silence. It is so easy to panic here, check the latest application commits, and blame a bad code push. But a senior engineer knows that an unhandled exception in Java or Node would leave a stack trace in standard out. Since the logs are totally empty, the application didn't crash itself. The system itself is the executioner. The culprit here is almost always exit code 137. The Linux kernel's OM killer, the out-of-memory killer, is violently terminating the container process without a single warning because it violated its memory boundaries. The app doesn't even get a millisecond to write a log. It's just assassinated by the host operating system. Reading these container exit codes is exactly how you diagnose infrastructure murder. And this leads right into another fascinating nightmare, the hot pod paradox. Your Datadog dashboard tells you everything is perfectly fine. You've got 10 replicas behind a load balancer, and the average CPU across the whole service is a beautiful, healthy 15%. But
10% of your users are getting massive 504 gateway timeouts. Why? Because 9 of your pods are sitting completely idle, and one single pod is pegged at 100% CPU.
We know this isn't just one massive user request taking down a pod. If you were using gRPC or HTTP/2, this is a classic Layer 4 load balancing failure. Because these connections are multiplexed and long-lived, a standard Layer 4 load balancer just opens a persistent TCP connection to one pod and stuffs all the traffic down that single pipe. So all your requests get permanently glued to one container, melting it down while the rest of your cluster literally does nothing.
Section 4. The Delivery Engine. Immutable Artifacts and Builds.
This brings us to the deployment pipeline itself, and arguably the most dangerous lie in DevOps, the pipeline that proudly reports a green success while production is fundamentally broken. Consider a catastrophic case of artifact drift. You meticulously test version 1.4 in staging, and it passes 100% of the checks. You promote version 1.4 to production. The application runs, but the brand new feature you just deployed, it's missing. Both environments display the exact same v1.4 tag, but production is somehow running the old code. A junior workflow might optimize the Docker build cache to shave 5 minutes off the pipeline execution, relying on mutable tags and shared build environments. But we discovered this creates a dangerous race condition where a newer, broken build can silently overwrite an image tag in the registry. Senior engineers, on the other hand, enforce hermetic, isolated CI/CD runners. They do this to prevent environment drift and state leakage, prioritizing absolute determinism over a slightly faster build. So how do we actually fix this? You must strictly build the Docker image exactly once in an ephemeral, hermetic environment. Then you completely abandon mutable tags like latest or v1.4. Instead, you pin the exact SHA-256 cryptographic digest of that image. Finally, you deploy that exact mathematically guaranteed hash predictably via GitOps admission controllers. We shouldn't care about the name of the version, we only have to care about the undeniable integrity of the hash.
Section 5. Master the systemic trade-offs. Performance is a systems property. Let's be completely real for a second. Every single architectural fix in distributed systems requires a brutal compromise. There are no perfect solutions, only trade-offs you choose to live with. For example, earlier we talked about the OM killer executing your pods. You can stop that easily by setting your Kubernetes CPU and memory requests exactly equal to your limits. But the trade-off? You directly destroy cluster bin packing. You essentially force your company to strand millions of dollars in unused RAM, paying cloud providers for gigabytes of empty space just to buy stability.
Ultimately, surviving at scale comes down to acknowledging this fundamental law of software engineering. Every line of code you write will be read 10 times, modified 3 times, and debugged twice. Before you write new logic or bolt a new tool onto your pipeline, you really have to ask yourself if you're willing to pay that ongoing maintenance tax.
Elevating your perspective as a senior engineer means recognizing that human deployment bottlenecks, configuration drift across environments, and silent infrastructure failures are just as solvable as standard application bugs. You need to optimize for deep observability, deterministic system flow, and hermetic delivery, rather than just obsessing over local code execution.
So, I'll leave you with this to think about. Take a hard look at your own architecture. Look right past your perfectly green unit tests and ask yourself, what part of your CI pipeline or your Kubernetes cluster is quietly waiting to take down production today? Drop your absolute worst production nightmare stories in the discussion below. Thank you for joining me for this explainer. Keep learning, keep deleting code, and I'll see you next time.